Now, let us see the concept of nuclear magnetic resonance spectroscopy, especially with H1 and C13 spectral techniques. How it is useful in elucidating the structure of organic molecules. First, let me understand. Here, the title itself is telling us the meaning of this spectroscopy: nuclear magnetic resonance. So, previously in UV spectra, it is in the electronic excitation level, and next to that UV spectra, we have seen infrared radiation. There, it is in the bond vibrational level of studies. Now, in this nuclear magnetic resonance spectroscopy, we are going to in depth when a strong magnetic field is induced against this kind of H1 and carbon-13 isotopes, which is present in an organic molecule, is introduced in between the two magnetic field. There is the absorption of radio frequency waves from the magnetic field of induction, is making the nucleus to undergo a spin lattice relaxation and spin relaxation of neighboring protons and carbon atoms. Here, the basic requirement for a nucleus to be active in NMR spectroscopy is that atom or isotope should contains the spin integral number I value should be more than 0, should contain more than 0. Then only those kind of isotopes are active in the magnetic field, so that we can gather the information about proton environment of an organic compound and carbon skeleton information from the C13 spectroscopy. C13 spectroscopic data. Here in this table, it is given that mass number and atomic number of that particular isotope of different atoms. All these things, all these isotopic atoms, if it is present in an organic molecule, those respective NMR can be activated to study the structural properties. And so this is the normal spinning of a nucleus. Normal spinning of a nucleus, this is our spinning nucleus. It is an axis which is in perpendicular mode against the magnet, along with its own magnetic dipole. And also its motion may be in any direction in absence of external magnetic field. If the same nucleus is introduced in an applied magnetic field strength, then these nucleus are undergoing a change in its spin inversion. Some of these nucleus are aligned with the spin integral value I in the alpha spin state. Some of them are excited to the beta spin state. So this kind of excitation de-excitation process makes provide us the information about the spectral evidences. So here the same information, which is expressed in the form of a formula 2i plus 1. And if we go for the spectral data, the application oriented part of this NMR spectral data, there in the NMR spectra we will use tetramethylsilane. TMS is one of the compound 4 methyl groups surrounded with the silicon. That is a compound called tetramethylsilane, used as a reference standard, that is the 0. From that 0, all the different types of protons. Protons may be available in the form of alkanes, alkynes, and then aromatic protons, and the functional group containing aldehyde protons. So these different types of protons are differentiated from the zero. The zero is nothing but the absorption position of the tetramethyl beak, and the measurement is carried out in this NMR in the form of parts per million ppm range based upon the magnetic field strength which is applied in the NMR instrument. And what is the interesting aspects of tetramethyl? It is chemically inert. It will not react with our organic molecule while it is mixed to record the NMR, and it is volatile. Its boiling point is very less. And after recording the NMR, if you just transfer your substances in a separate vial, and if you just evaporate your solvent, then automatically you will get back your compound. You can recover your compound. It gives a single sharp and intense peak for 12 protons. It will give you 12 protons in a single peak. So it will be the max. It can exhibit the maximum intensity in the zero, and these protons are absorbed in higher field. In higher field means all other protons which is in the form of organic compounds, or one or two exceptions are there. All of them are coming after the absorption position of the tetramethylsilane, and then it does not involve in intermolecular association with the compound which we are recording for the NMR data. And finally, it is soluble in most of the organic solvents. So we can use all sorts of deuterated solvents like CdCl3, deuterated DMSO, deuterated benzene. All sorts of these organic liquids are soluble with TMS. That's the importance of tetramethylsilane used as a zero or reference standard in the NMR spectroscopy. And how to measure? What do you mean by chemical shift? Chemical shift, the definition of chemical shift is nothing but the absorption position of a particular proton of our new organic compound with respect to the absorption position of tetramethylsilane. That is called chemical shift. From 0 to how much it is downfielded shift occurred for a particular proton which we are recording for the NMR data. So here the data is expressed in the unit of delta, and the unit is ppm, and the formula which is used for getting this delta value for a particular proton is chemical shift in hertz and oscillator frequency in hertz into 10 power 6. And here oscillator frequency is in hertz. So likely if you just apply this formula, delta is equal to a peak at 60 hertz from TMS at an applied frequency 60 megahertz would be at 1 or 1 ppm, delta or ppm 1. The formulas, if you apply those values in this formula, we will get the same 1 ppm. And here another one concept which is more important in elucidating the structure of NMR. See, look at the molecule of olefin. Here, when we apply this double bond containing organic molecule into the applied magnetic field strength, then there are two regions were generated. One is shielded region against the applied magnetic field. Other one is deshielded region against the applied magnetic field. If deshielding is occurred for a particular proton, that will go to the downfield shift or far from zero. And if a proton or carbon falls on the shielding region, then that absorption position of the particular proton or carbon which is falls on the upfield with respect to the TMS reference 0. and this table shows the different types of absorption positions of different protons present in different types of compounds. For example, the region between 0 to 1 is meant for alkyl based groups, and then next to that, if we go for 2 to 3, 3.5, that proton containing carbon, if it is substituted with halogens or ketone or ester groups or OH, there the downfield shift is occurred for the particular alkyl group because of the electron training effect exhibited by the chlorine halogens as well as this functional groups. And the olefinic proton range falls between 4.5 to 6.5 region, and if it is substituted with the different types of electron withdrawing functional group, again it may go beyond that level also. That is the concept of shielding and deshielding effect of different groups which is attached to the particular hydrogen or carbon. And then the ppm level between 6.5 to 8.5, which is responsible for the appearance of aromatic ring containing protons, and also functional group containing allylic protons falls between 9 to 10 ppm range. These are all the overall table for the different types of protons which is observed in the NMR spectra, and using this kind of shifting positions and other values we can elucidate the structure which we have taken for our compound. Then this is the relative intensities for splitting of signals. For example, if this is the situation, for example, if we have only methyl group alone, so all the hydrogens are placed on the same carbon, so all are in the same environment, so they will be appeared in the form of singlet, which is designated as S. Singlet means we will get only one single peak, nothing splitting will be occurred in the peaks. And then if your hydrogen is substituted next to a carbon containing with a proton, then that proton is called neighboring proton. That proton is called neighboring proton. We are getting information for the first hydrogen atom, and it contains one neighboring proton. Then you should consider all the hydrogen present in the same carbon as one, and the number of neighboring protons as n. If we have only one proton here, so 1 plus n. Here we have one proton, so 1 plus 1 is 2. So the splitting pattern for the first proton will be appeared in the NMR spectra as a doublet, that is designated as D. And if your proton is substituted with 2 neighboring protons, then 1 plus 2, it is 3. So we will get a triplet, 3 big splittings for the single proton. And if your proton is substituted with 4 different neighboring protons, whatever may be the situation, then you will get quadret. And the relative intensities, if it is intensity means the big height. The big height is whatever be the maximum for a singlet, it will be in the same intensity. If it is a doublet, both peaks will be in the same height, same intensity. And if it is in the triplet form, the first peak will be in one height, second peak will be exactly 2 times, and the third peak will be again 1 time. So it is a triplet. If your proton contains 4 neighboring protons, 3 quadret, that ratio is between 1:3:3:1. So first peak will be appearing one small peak, and 3 times higher than that, again 3 times, again single. That type of peak splitting is called quartet. Then pentet. Again, this rule is called Pascal triangle to determine the different types of splitting pattern for a particular proton in the NMR spectra. Here, you just take a look of the spectra of ethanol. Here, take the it is a OH proton. It is a PMR, means proton magnetic resonance spectrum of ethanol, neat acidified at 60 megahertz. It's a the OH group is appeared in the form of singlet. Even though it contains two neighboring proton, it cannot be seen here. And the next CH2. For this CH2, we have 3 methyl group proton as a neighbor and one 3 plus 1 for the CH2. So we are getting the CH2 peak in the form of a quadrette. And for this methyl group, all the 3 will have 1, and the remaining 2 neighboring protons, 1 plus 2, which is giving a triplet. You just look at this Pascal triangle explanation. Exactly this peak position for triplet, one level, and exactly equal to 2 levels, 1:2:1. Here 1:3:3:1. And next to the concept of coupling constant. This is also one of the most important points to be noted. That is called J value. It is nothing but the distance between the centers of 2 adjacent peaks in a multiplet. Multiplet means tetraplet, triplet, quintet, like that. Is called coupling constant or spin-spin coupling constant, J value. This J value is used to always quoted in Hertz value or cycles per second, and it should not be considered the ppm value. And it is very well used to distinguish cis-trans isomerism. Here we took E isomer, that is the trans isomer of 3-chloropropenoic acid, and Z isomer of 3-chloropropenoic acid. Here the splitting pattern is occurred similarly, because for this proton only one neighbor, for this proton only one neighbor. So 2 doublets we could be able to see that. And among the 2 doublets, if you measure the coupling constant for trans is nearly more than 10. It reaches maximum of 14 Hz. And for coupling constant of your cis isomer, it falls between 0 to 10. So these are all the relationship to distinguish the cis-trans isomerism using the coupling constant value. Then generally trans isomer will have more coupling constant value than the cis isomer. And next, if we go for C13, the range between 0 ppm to 200 ppm. Here, instead of carbon, we should imagine the instead of hydrogen atom in proton NMR. Here it is the instrument is measuring the carbon atom present in alkyl group and CH2 group and polyphenic carbon as alkyne carbon, and then aromatic and heteroaromatics and functional group containing COH carbon, and then quaternary carbons and ketone containing compounds. All these ketone carbons, all these different types of carbons are measured broadly between 0 to 200 ppm. And now let me conclude it. All these things by taking one of the example from my research and using these all kind of spectral interpretation during my research in synthetic organic chemistry. Here is the compound which contains one double bond with hydrogen and substituted with 2 sulfur, benzyl group with 2 chlorine substitution. And the field is nitrogen star. And if you record the NMR, this was synthesized in the laboratory, and if we record the NMR for this compound, it gives here 2 lambda max peak values. One is for the lone pair of sulfur atom, the lone pair of electron present on the sulfur, which is involved in the resonance with the nitro group, the through extensive conjugation. That extensive conjugation was measured was observed in the form of the peak value appeared in 361 nanometer, and this one is for the presence of this aromatic ring system. Like this new compound was interpreted with UV spectral data. Next to go for IR, we will have nitro group as a functional group. So here 1530 and 1436 which is substituted with olefin and two sulfur atoms was measured here. And then in this NMR, in proton in H1 NMR, we have olefinic proton here and CH2 proton, two CH2 groups here, two CH2 protons and aromatic ring protons. The two CH2 protons, here there is a difference. Actually, this molecule is unsymmetrical. So this CH2, which is trans, which is E to this nitro group, is observed in downfield shift of 4.62, and which is Z2, this CH2, which is cis to this NO2 group, is observed in the range of 4.578, and the olefinic should appear between here in 6.5 because of the presence of strong electron decline nitro group in this molecule. The absorption coefficient is downfiltered from 6.5 to 7.2 region, and which is merged with these aromatic protons. And here also we could be able to see this one two CH2 group, that is CH2 alkyl part groups. There also we could found 36 is responsible for the CH2 carbon trans to the nitro. 32 is responsible for the CH2 carbon, which is cis2 nitro group. Here this is for CDC3, and here 127.63 is assigned for this olefinic carbon and olefinic carbon, CH carbon. And then here if you just look at all the aromatic protons and the quaternary carbons, quaternary carbon which is present here was appeared in the range of 161 ppm. And some of these MRI applications, all these techniques basically arised from this technique of nuclear magnetic resonance spectroscopy. And finally, thank you very much for your patient hearing. Once again, I thank all the organizing committee of this faculty development program by Arulmigu Palaniyandavar College, Palani, and my sincere thanks to the principal and HOD and the organizing secretary, Dr. Manimegalai Madam, for inviting me to share some of my ideas in the topic of spectroscopic tools for organic chemistry. Thank you, one and all. Thank you.